support vector machine that we are going to learn today. So don't worry about that. The major use of this is classification. So we are going to learn how it is used to do that. Acha chalo, second question. If I give you, let's say I change the axis to this. So we have added a dimension, third dimension, to make the data linear. So this is about the kernel trick of support vector machine, using which it is capable of. Okay, so we'll start with the lecture today. It's support vector machine that we are going to learn today. Today we are going to learn another algorithm known as support vector machine, which is originally designed for classification. But nowadays, like all the classification algorithms can be used for regression also. Like there is random forest regressor, support vector regressor, and so on. So don't worry about that. The major use of this is classification. So we are going to learn how it is used to do that. So let's say we have data like this. Okay. So Y is our classification target, and it can contain 0 or 1 value, let's say. So red represents Y equal to 0, and blue represents Y equal to 1. So will logistic regression be able to classify this? This is the data you can see on the board. This is exactly what the data is. Will logistic regression be able to classify this? So yes, that's the very simple answer. That how can it divide? Like it cannot divide like this, like this. There's no way. Like it will create a boundary which has the minimum loss, but the minimum loss will also be very high, because logistic regression model is not made for non-linear data. Okay, it is built on the assumption that your boundaries are linearly separable. Okay, so what should we do with this? What should we do? But can you guys think like what kind of boundary is required here? Acha chalo, second question. If I give you, let's say I change the axis to this. Let's say this is the center and it's around this. Okay, this is x1, this is x2. If this is the data, will you guys be able to solve this using logistic regression? Like after some data, whatever steps you want to do, I just want to solve this with logistic regression. How can I do that? Can you see a possibility of generating a linear boundary here? Hint is feature engineering. You have to do something with your inputs. Okay. So answer is very simple. I will just create a new dimension called x3. Okay, x3 will be, let's say, x1 square plus x2 square. If I create this dimension x3, so what my data will look like is, so from the center, it will basically take the distance. That's it. Okay, so if I take this point, let's say this point is 3, 4. So this point will be, I do under root. So if I take 3, 4, this point will become 5. X3 will become 5. Okay, so you will create a new dimension which goes in the z direction. Let's call this x3. Okay, so x3 will be equal to 5 at this point. So x3 will keep on increasing as we go far from the center. Getting my point? Now it became a linear separation with respect to x3. You can clearly see that, let's say this is the boundary. This is the boundary. So this boundary, we can think in terms of x3, that this boundary can be x3 equal to 7, let's say. Okay. So if x3 is less than 7, it's red. If x3 is more than 7, it's blue. Did you guys get this? So now the maths behind support vector machine is complicated, so I won't be getting into that very much. I'll just tell you the gist of it, see what happens. Okay, loss function I'll go through nicely, but the actual thing. So the main thing that it's famous for is known as kernel trick. Kernel trick. Okay. So currently what you did was you had a two-dimensional non-linear data. What you did, you added a dimension. So your data became three-dimensional linear data. Okay. Yeah, one more step, guys. So we found this boundary. This is the boundary. X cube, x3 equal to 7 is the boundary. Now, if I convert back to our normal data, x3 equal to under root of x1 square plus x2 square. So if I'll say boundary becomes this, boundary becomes this. I will then remove my third dimension. Okay, I found my boundary, then I don't need this new dimension. All I just needed it to find a linear boundary, that's it. Once I found this boundary, I will revert back to my original columns, which is x1 and x2. Okay, so now whatever input comes up, I can easily find which class it is. Okay, using this formula. Okay, so that's how it is. And yeah, we can see that we have found a nonlinear boundary. So we have added a dimension, third dimension, to make the data linear. Find linear boundary for 3D data. Convert back to nonlinear boundary for 2D data. Okay. So this is the process. We have x1, x2. We created x3. If found the boundary which was x3 equal to 7, and we converted it back to the 2D nonlinear boundary, which is x1 square plus x2 square equal to 49. Okay. So this is the normal process that we will have to do, and it's a very tedious process. Like, first of all, this case was very easy that we were able to visualize this. Okay. Normally there will be tens or like 10, 15 columns, even more. This is like less I'm talking about. So you won't be able to visualize this. You don't know how to add the new dimension. Okay, it will be very confusing. So support vector machine handles that. Okay, it just gives you this using kernel trick. You don't need to worry about all these things. Okay, if you use support vector machine. Okay, and you have to mention one hyper parameter here that you will be tuning when training support vector machine. It will be known as kernel. So this, if you have a circular kind of boundary, you will say kernel equal to RBF, which is a radial basis function, I guess. Yeah, RBF. Okay, so there are other kernels also. We'll learn that we can look that in the documentation of support vector machine. But yeah, if you mention this thing, kernel equal to something, it will give you non-linear boundary accordingly. Okay, if you want circular boundary, you will say kernel equal to RBF. So it will give you this kind of boundary. So this is about the kernel trick of support vector machine, using which it is capable of identifying non-linear boundaries also. Okay, it's a very powerful tool.